Hey everybody, I am back and I am here to record part two, the second video to chapter four. This one's going to focus on proteins themselves. So last time we talked about really more about the building blocks of proteins. We talked about amino acids and looked at their features and structure very carefully. And so now we're going to look a little bit more at proteins themselves. Okay. So I want to preface this by saying I took the sort of the stock PowerPoint like I did previously. I took the stock PowerPoint and added some other slides that were based on the other book. For some reason, a lot of the pictures that are in those will not. My iPad can't handle the size of them or something. I don't know, because you'll see a number of them. I'm going to skip ahead here. Like this one, for example, they get cut off. So as I'm narrating it, that's going to be a little problematic, because if you're just watching this video, as I'm going to it, I can't see the whole picture on my screen. I've got a book over here that I'm using to help me sort of get through the explanations and all. But as you're watching this, for you to see really see the whole picture, you will want to either have the PowerPoint up on a real computer. This displays fine on my laptop or my PC, so it's just my iPad doesn't like it for some reason. So I would recommend, before you get into this video, make sure you have either the PowerPoint open on another computer, or you have the PDF of the alternate book handy. Because a lot of these pictures came out of that alternate book, and you can look at it in their chapter 4 to find it. So, give you a second here, go ahead and pause it, get whatever you need ready, and then we'll dive in. Alright, let's get started. Okay, so we're talking more about proteins themselves now, and so when you talk about proteins, you actually have sort of 4 tiers or 4 levels of organization and structure that you're looking at. You have what we call primary structure, secondary structure, tertiary structure, and quaternary structure. All right, so we're going to go through each one of these here and talk about the basics that are involved in formation of these structures, and also look deeper at some of the features, and also look at some examples in each case. All right, so I want to start with primary structure. This is the most basic baseline type of structural analysis you can do with proteins. This just simply defines the structure, or excuse me, the sequence of amino acids, right? What amino acids are in the protein chain and what order are they in, right? They're always described, as we said before, going from the N-terminus in to the C-terminus in, all right? And so if you're defining or outlining, what a sequence of amino acids is, then you can typically represent them by either their 3 or their 1-letter designations that we mentioned in the previous video. Here's an example. This is actually not a protein, but this is what we call an oligopeptide. An oligopeptide is weird. Is sort of the in between. It's not quite big enough to be a polypeptide or protein, but it's not small enough to be like, dipeptide, tripeptide, etc. So anyway, this just sort of shows you how the sequence of amino acids are written. At the N-terminus end, we would have glutamic acid, and at the C-terminus end, we would have cysteine. This particular one is something called a conotoxin, produced by certain snails to paralyze their prey. Interesting. I didn't know that myself. So, there you go. Lots of interesting applications of peptides and proteins. All right. This sequence, like I said, is very much the baseline identity of a protein or a peptide. You change even one of these amino acids, that's going to change the nature of your peptide. Sometimes it has virtually no real life effects or very minimal, and then other cases it makes a big difference. All right. So, just a couple of examples. Here's a couple of peptides. Each of these is going to be 9 amino acid residues long. These are a couple of hormones present in the human body. One of them is called oxytocin. That's going to be the one on top. Oxytocin has a few different functions. It's used a lot in both prenatal and postnatal functions. It's a hormone that can stimulate the contraction of the uterus during childbirth, and also can help stimulate the production of milk when nursing. Also, it's kind of informally known as the love hormone. Uh, not romantic love necessarily, but more just kind of like security and happiness and contentment. You see, and this is associated somewhat with the nursing aspect, but also anytime there's sort of a bonding in that occurs within mammals, not just human beings, um, you can have an oxytocin release that makes you feel nice and loved. This is actually pretty common in. You see this with cats and dogs, right? A lot of times, cats and dogs will like to gaze into your eyes, and that's considered a sign of affection because when they do that, when you and your pet gaze into each other's eyes, it stimulates a release of oxytocin in them and often in humans as well during the process that really sort of helps strengthen that bond. So, kind of cool. Vasopressin is another 9 amino acid hormone. So this one's got an entirely different function. This regulates water in water reabsorption in the kidneys. Right, kidneys will filter the water, and some of the water that gets filtered out can be reabsorbed by the kidney for use. And so vasopressin can help stimulate this reabsorption. If you look at their sequences, they're pretty similar, right? They're both 9 amino acids long, and they almost completely match as far as the sequence. There's only two real differences. At amino acid residue 3, you have an isoleucine and oxytocin versus phenylalanine and vasopressin. And then at amino acid 8, you have a leucine and oxytocin and arginine and vasopressin. So, the book proposed here a question. Identify the difference in their amino acid sequences. Well, we just did that. And determine which hormone is more soluble in water. Well, yeah, if you have a difference in amino acid sequence, then solubility in water is one of the many things that can be affected, right? So if we look at this, we're trying to figure out what's the effect of solubility. Well, let's look at each of the pairs of amino acid differences and kind of see what we can come up with. All right. One difference is at amino acid residue 3, isoleucine versus phenylalanine. All right. I don't have the amino acid chart handy here, but you guys can look it up. Um, this substitution of phenylalanine versus isoleucine, that wouldn't really make much of a difference as far as water solubility because they both have very, very polar side chains, right? Both of them are hydrophobic. So they both kind of like to dissolve in the same things. However, if you look at leucine and oxytocin versus arginine and vasopressin, and I have these in my notes here, I'm going to draw them out. In leucine, I'm just going to draw the side chains attached to an R group here. Leucine you have a very hydrophobic side chain. Very nonpolar, very hydrophobic. And if you look at arginine, That's a positive charge. All right, arginine is very different, right? It's got this big polar portion over here that actually can even acquire a full charge under the right conditions, right? So this one has a very hydrophilic side chain. All right, so because of that, the one with arginine, which is vasopressin, it's going to have extra water solubility. So, extra water solubility can affect where it is going to be in higher concentrations in different areas of the body, what membranes it can cross, and what substrates it can interact with, right? So that's just one example of how even a single amino acid residue can change the properties of a protein or a peptide in this case, right? In this case, the solubility has a lot to do with it. Another good example is in a condition called sickle cell anemia, and you've probably heard of this. I'm willing to bet you talked about this in genetics before. Of course, sickle cell anemia is a genetic disease which causes red blood cells, which are normally kind of this, sort of this disc shape, to accumulate in more of what we call a sickle shape, right? And you can see an example of a sickle cell right over here compared to normal red blood cells, right? And that's bad, right? Because when red blood cells are in the sickle shape, they can't carry oxygen nearly as well as the regular red blood cells. They're not nearly as efficient. So if you have sickle cell anemia, the various parts of your body are going to have trouble getting oxygen. Excuse me. All right. Why does it do this? Well, this all has to do with hemoglobin. Hemoglobin is the important protein that is in red blood cells that helps to carry oxygen around to the different parts of the body. And we'll talk a lot more about hemoglobin later on. But it's a large protein with multiple subunits, right? So this is considerably larger than vasopressin and oxytocin that we talked about earlier. And it has one particular substitution that causes this problem. All right, we're going to see hemoglobin actually has what we call subunits later on. That's going to have to do with quaternary structure. But in certain types of subunits, the beta subunits, there is one substitution. You have a valine that is put in place where glutamic acid is normally located. All right, let me show you what that looks like. All right, so this is what's normally present. Normally you have a glutamic acid residue in hemoglobin at that position. All right, so again, I'm going to just draw the side chain here. All right, and as you can see, this side chain is quite polar, right? This is one of our amino acids that can actually have charged side chains under the right conditions. Yeah, very polar, very hydrophilic. All right. Valine, on the other hand, has this group, has an isopropyl group as its side chain. All right, this is very nonpolar, very hydrophobic. That says hydrophobic, even though I butchered it with my terrible handwriting, so sorry about that. All right, so valine's present here where it shouldn't be. And that's important because hemoglobin, much like any other protein, has a very particular folding pattern. It may look like in models like it's just a crumpled up sheet of paper, but there's a very intentional folding pattern that occurs. All right, and so what happens is this residue number 6, comes in close proximity with two other amino acids in the folding process. All right, when hemoglobin is folded normally, that amino acid residue comes in close contact with both phenylalanine and leucine. All right. If you look at these, and I don't have the structures handy right now, but you guys can look them up on your table. If you look at phenylalanine and leucine, these are both going to have very hydrophobic side chains. So here's where the problem comes in. Normally, you have glutamic acid in close proximity with phenylalanine and leucine. That's fine. That's perfectly good. There's not a real attraction between glutamic acid and then these two other side chains because one's hydrophilic and the other two are hydrophobic. However, in sickle cells, if you have valine, that means you're putting a very hydrophobic residue side chain in close proximity with two other ones that are also very hydrophobic. And they're going to have sort of an attraction to each other, right? They're going to want to stick together a little bit more than they would have if it was glutamic acid. All right? And therein lies the problem. In sickle cell anemia, you have this extra stickiness, this extra agglomeration that occurs between hemoglobins, individual hemoglobin molecules. They sort of stick together and they kind of glump together and they basically polymerize, not really through a chemical interaction, but more a physical attraction, right? And so they bunch up, and as they do so, they'll acquire this characteristic sickle shape. And they really lose their function. And that's bad because that's very, very dangerous. All that is, again, this just serves as a good example of just how much one change in your primary structure sequence can have an overall effect on function of the protein. All right, so that is primary structure. Secondary structure digs a little deeper. Secondary structure is really talking about the backbone, the overall backbone of the peptide chain. And this is where we refer back to the formation of peptide bonds, right? We talked about how when we form a peptide bond, the carboxy terminus of one amino acid forms the peptide bond by reacting with the N-terminus of a different amino acid. And this just keeps going and going as you add links to the chain. So what you end up with is this backbone that forms the backbone of your chain that's composed of these peptide bonds. And then you have the individual amino acid side chains hanging off. So, when talking about secondary structure, we're worried more about this backbone and not so much about the side chains. All right? So we've talked about this a little bit, right? We know whenever we form a peptide bond, that CN bond that we make, that has partial double bond character, right? That means there's no free rotation around that carbon-nitrogen bond. That makes it have the peptide backbone have a certain amount of stability. You do still have some other single bonds within the peptide backbone that can rotate, right? So it's kind of a balance here. You have some mobility, but it's limited. Basically what the protein chain tries to do as it folds, it tries to fold so that the polypeptide backbone can have the best optimization of hydrogen bonding. In a nutshell, again, I'm going to sort of represent it over here. let's say that this line represents your protein chain, your polypeptide chain, right? Specifically the backbone. This is going to represent the backbone. And, this protein's going to fold in certain ways, right? This is one example, right? It wants to do this in a way that you can make hydrogen bonds very efficiently between different areas of the backbone. Like that, right? The more efficiently that you can make hydrogen bonds, the better the protein backbone can be held into place, and that gives it more stability. All right? So that's what secondary structure is all about. It's all about finding these ways to take your backbone and connect them well through hydrogen bonding. And there's multiple ways of doing this. There's several different ways. However, there are a couple of regular secondary structures that tend to pop up much more than other ones. And you guys have probably heard of these before. The first one is called the alpha helix. All right. The spiral. I would say it looks like a telephone cord, but man, you guys are probably way beyond that. So if you have to Google a telephone cord, look at it. But in a nutshell, it's got these nice little spiral patterns. All right. And this photo, you can kind of see it highlights that, just like we mentioned, this is designed to promote the creation of hydrogen bonds between different parts of your backbone chain, right? So you see the little red balls, those are oxygens. You can see a hydrogen bond here forming to the little white ball. That is a hydrogen. That's one on one of the blue balls. That is a nitrogen, right? Here's one representation, and here's another picture I got from the other book that also kind of shows this in different manners. You can take a look at them. They can offer different perspectives. Couple of quick facts about the alpha helix. Hydrogen bonding is arranged so that the carbonyl groups that are present in the backbone will hydrogen bond to NH groups that are 4 residues away, right? That's a consistent pattern that you have. 4 residues between hydrogen bonded species. For every turn of the helix, right? That's for every little coil that it makes around. There's an average of 3.6 amino acid residues per turn, and the pitch is 5.4 angstroms. What the heck is the pitch? A pitch is just the distance between corresponding areas from one part of the turn to another. So you can kind of see it in this photo over here. 5.4 angstroms. Okay? So, yeah, you have these little alpha helices. That's my very detailed representation of an alpha helix. I hope you can appreciate that. But very, very regular, very patterned, a lot of repeating units. All right. Now, it's regular, but there are things that can disrupt it, right? Whether these things are meant to be there or not meant to be there. Sometimes these disruptions are present because there's been damage to the alpha helix or some sort of mutation that occurs. But there are certain things that can disrupt the regularity of the patterns in an alpha helix. A couple of them. Number one, proline. The presence of proline in an amino acid sequence can cause an alpha helix to maybe look a little bit different than it normally would. Why? Well, let me put up the structure of the proline again. All right, remember proline was kind of the oddball of the 20 essential amino acids. It was the only one that had the side chain actually sort of loop back and bond intramolecularly. All right, that's proline. Side chain loops back and bonds with the amino terminus. All right, it's the only one that does that. So it forms this ring structure, this sort of oddly spaced ring structure that, for lack of a better description, it can just sort of cause little kinks in the chain. It can cause little bubbles. Yeah, just the weird shape of this group here can cause little kinks, bulges, whatever within a polypeptide chain. And if you're turning this into a helix, this could cause like one of the loops to kind of, jut outward or jut inward, maybe a little bit more than it usually would. Also, sometimes we haven't really talked about side chains, but if you have a bunch of charged side chains that have similar charges on them, that can cause a little bit of a disruption, right? Because if you have a side chain, let's say you have two positive side chains that are in close proximity when the helix coils, those like charged side chains, they're going to repel each other, right? They're going to want to try to get away from each other, cause more space in between them, and that can cause a little bit of a disruption in the regularity. If you have a whole bunch of bulky side groups in close proximity, this can be any of the ones that have large ring structures, like big aromatic rings such as tryptophan, phenylalanine, tyrosine, something like that. If you have big bulky side groups, those can sort of get in the way and again cause a little bit of a disruption to the normal coiling pattern. That is caused by steric hindrance, which is a phrase we use a whole lot in organic chemistry. All right. Okay, the other really commonly found secondary structure is beta-pleated sheets. And again, you've probably heard of these. This is a little bit different. If instead of taking a protein chain and sort of coiling it up, where you're kind of bunching it up a little bit, in this case, you're stretching the chains. You're taking them and you're spreading them apart as far as they can go. They're going to be extended, and they're going to form these sheet-like structures. All right? So, if an alpha helix, looks something like that, a beta sheet would be more something like that. Okay? Okay. So, just like with alpha helices, beta sheets are also entirely dependent on hydrogen bonding. And these can both be what we call intrachain bonds, or if there are interchain bonds. So let's say, I'll just draw that thing I just drew, right? So you had one sheet like that, and it was kind of extended in this manner. You could have hydrogen bonds between different areas of that same chain. These are going to be intrachain hydrogen bonds, but you can also have different beta sheets that are also hydrogen bonded to each other, right? These are going to be interchain. All right. All right, so we have those two types of hydrogen bonds. We can also have a couple of different arrangements. We can have what we call our parallel arrangements or our anti-parallel arrangements. All right, so this basically means if you have multiple chains, do they run in the same direction or do they run in opposite directions? And this is all in terms of termini, right? So, if you had two beta sheets and they were aligned like this, that would be parallel. However, if they were opposite, that would be an anti-parallel arrangement. Okay. Either way, you can get hydrogen bonding. So this shows you a couple of different. I just now noticed this show. This shows two anti-parallel. I don't know why they did this. Anyway, okay, sorry, I'm just now noticing this. So this picture is somewhat less useful now. I was assuming that it showed one of these as being parallel and one anti-parallel. So Google it. You'll find plenty of photos of this where you can have a comparison of the hydrogen bonds that you make when you're in parallel arrangements versus anti-parallel. The anti-parallel arrangement is usually a little bit more favored as far as optimal hydrogen bond alignment. The angles of the hydrogen bonds are a little bit straighter in anti-parallel arrangements, so they're a little bit easier to form. All right. So yeah, those are going to be the two most common regular secondary structures. Now you do have other secondary structures that do occur. A lot of them are what we call irregular. They're not necessarily in a certain pattern, but they're just kind of there. Right? So, and that's perfectly normal. They don't have to be in a helix or a sheet or any other regular arrangements, but you do have other regions of irregular structures that occur sometimes. Anytime there's a loop, right? And you can see here, in each of these cases, you have, in the first case, you have an anti-parallel beta sheet arrangement, and in the second one, you have a parallel arrangement. But in either case, you have these little connectors, right? That sort of, connectors that connect, yes, the two different areas together, right? These are going to be less regular structures. Frequently, when you have a sudden change in direction, such as in this first picture on the left, that forms something called a reverse turn. The chain, as it's folding, is going one direction, and then it's going to loop back and go another direction. These reverse turn segments will help the chain kind of fold in the right direction. All right? A lot of times they'll represent a transition from one helix to another helix, or one sheet to another sheet, or from a helix to a sheet, right? There are a couple of amino acid residues that you commonly find in reverse turns. One of them is glycine, right? Glycine is very commonly found in reverse turns. Why do you think that is? Maybe pause it. Give it a second to think about it. Why would glycine be really good in reverse turns? Spoiler, I'm about to tell you. All right, so if you're making a sudden change in direction, it's literally, you can kind of think of this like driving a car. You might have to, get to a hairpin curve that you have to slow down and then very carefully go around because it's a very tight squeeze. You have a very small area in which to sort of arrest your momentum and get going into the other direction, right? Same thing here. These could be very narrow, very quick changes of direction. So having something like glycine is very helpful there because glycine has the smallest side chain of any amino acid. Its side chain is literally a proton. It's an H. Because of this, glycine doesn't take up very much room, and it can fit in very, very well into making this tight, narrow change in direction. All right? We actually have 3 different types of reverse turns that are commonly found. Again, I'm sorry, my iPad has cut this off, but please feel free to look at this in the PowerPoint on the regular computer. You can see all of them laid out there. Type 1 and 2 are the ones that glycine is predominantly found in. I'm not really concerned about you knowing the differences between those two. I just kind of wanted you to know that type 1 and 2 reverse turns frequently contain glycine. Another one that's commonly found in certain reverse turns is proline, which we've mentioned before. Proline has sort of that wonky ring structure that connects its side chain with the amino terminus. It just so happens that that little kink, that little odd shape that's introduced, is actually very good in sort of forming the geometry necessary to loop back in a different direction. So, cut off here is a picture of the type 3 reverse turns. Those are the ones that commonly have commonly have proline in them. All right, let's see. Just a quick note, not only can we have regular patterns of secondary structure, helix, a sheet, we can also have what we call domains, also known as supersecondary structures. Basically, domains are common combinations of secondary structure that can also be found, right? So, for example, one of the common domains that is often observed, let me erase this, is commonly called the alpha-alpha. That basically means you have one alpha helix, reverse turn, joined to a different alpha helix, right? And so this collective combination of two alpha helices is called alpha-alpha. Another one is beta-alpha-beta. So let's say I might use the arrow to represent a beta sheet. You could have a beta sheet connected to an alpha helix bonded to another beta sheet, right? And collectively, that would be called a beta-alpha-beta. Kind of looks like a letter N. All right, there's another one called the beta meander. And this is where you have several beta sheets in an anti-parallel arrangement. And they sort of coil like a snake with reverse turns linked together like that. I'm just drawing these little patterns off to the right because that kind of shows you. Sometimes these are compared to sort of artistic things, and so my old book had them, so I was going to pop them in there for you as well. All right. And then this is my favorite one. My personal favorite is the Greek key. All right. This again has to do with anti-parallel beta sheets. But it's a much more exotic connection. Like you could have this one connected to this one over here. You could have this one and this one connected there. You could have this one and this one connected here. And so the pattern that it forms, I just messed it up. Looks sort of like this. And this is actually a common pattern that's found on a lot of ancient Greek artifacts, like vases and stuff. If you look in chapter 4 of the Campbell textbook PDF I put on Moodle, they'll have a picture of it. It looks pretty cool. But yeah, these are all these things are actually pretty common grouping patterns that you see a lot of times within proteins. All right. Let's talk about tertiary structure. Tertiary structure is where the side chains come in, right? So tertiary structure is a more holistic view of the folding patterns again. So secondary structure looked at folding patterns, but only incorporating the backbone, right? Tertiary structure includes not only the backbone, but also the side chains, all right? We'll discuss this one later, so I'm going to skip that slide for right now. But basically, we've alluded to this before. The function of a protein, its physical properties, everything about it, is really determined in large part by the overall folding patterns. There's lots of different ways to fold. Backbone interactions, backbone hydrogen bonding is important, but also interactions between side chains is important, right? And this opens up other possibilities besides just hydrogen bonding. Hydrogen bonding is certainly part of this as well, but also you have hydrophobic interactions that are important, electrostatic interactions and ion pairs, disulfide bonds, and a few others, right, that are going to be important. Here's a photo that I think does a pretty good job of illustrating some of these, right? So, within a tertiary structure, you could have any of these or all of these, or just a few of them, right? We mentioned hydrogen bonding, and you can kind of see, over here on the left-hand side, it illustrates the hydrogen bonding through these red dots or these little ladder rung things that happens between the backbones. So that's nothing we haven't seen before. But you can also have hydrogen bonding amongst the side chains as well. That's something we haven't talked about, right? So in this case, you see a hydrogen bond being made between the carboxylate side chain of one amino acid and then the OH group of another one, right? Hydrophobic interactions, right? We alluded to this a little bit with sickle cell anemia, right? So if you have side chains with a bunch of hydrophobic interactions, those can cause attractions. You can have metal ions that can be located within between different parts of the chain, and that can sort of link them together. One really common one, I think was mentioned before, I'm going to highlight here, is called zinc fingers. I don't know why they call it zinc fingers, but it's a fun name. But basically, in that case, a zinc would be right here where this metal part is, M2+, and that would help to sort of link or connect those different parts of the chain. Electrostatic interactions. Interactions between full positive and full negative charges, right? All of these that we've mentioned are various types of intermolecular forces, right? And these can occur in a variety of different ways with side chains. One additional thing that's not an intermolecular interaction, but this is a full-on covalent bond, can be the formation of what we call the disulfide bond, all right? And that specifically occurs between cysteines. All right. Cysteines, remember, within their side chain, cysteines have thiol groups, SHs. If you have two cysteines that are in close proximity to each other, these thiol groups can react with each other and form disulfide bonds. And that's what this is. Disulfide is SS. So that's the only part of these tertiary structure interactions that are not intermolecular forces. These are full-on covalent bonds. All right. So if your backbone hydrogen bonding sort of forms the framework for the folding, Tertiary structure interactions are what really fine tune it into the final arrangement that it gets in. Fun fact, a lot of these tertiary structure interactions can be disrupted. You can break them, right? Um, you can break them in several ways by heating them up. If you add enough heat to overcome the energy of attraction, then they can be broken. Changing the pH a lot of times will break these electrostatic interactions because you're changing the protonation state of side chains. Adding detergents, and also breaking disulfide bridges. You may ask, well, why in the heck would you want to disrupt tertiary structure? Well, a lot of times you actually think that in order to fully understand the structure of a protein and try to map it out, you will actually have to disrupt these interactions. That's called denaturing, because that makes it easier to analyze for the amino acid sequence. So there's one. There's one reason why. What's fun also too is that when you denature a protein, sometimes it can only be temporary. Sometimes they're reversible, right? So, for example, if you heat up certain proteins, it might denature them. They might go back to their original formation when you cool them down. Let's say you make the pH more acidic to break electrostatic interactions. Well, if you go back and adjust that pH to the original one, what it was before, then those interactions will return. Sometimes they're not reversible. Like if you break a disulfide bridge, you're probably not going to be able to make that again. So, like I said, probably the biggest application of that is when you're trying to really take a protein and kind of learn more about its structure and also its form. So you have to pick which types of denaturation you want to use, whether it needs to be reversible or not. Okay. Also, we can really start seeing physical properties develop now. All right, so when you look at the tertiary structure of proteins, excuse me 1 second. When the tertiary structure is formed, for the most part, you can actually classify proteins into one of two groups based off of kind of their physical properties. They can be either classified as fibrous proteins or globular proteins. All right. It really depends on whether the alignments between amongst the protein chains are sort of along a regular axis or something, or are they more random, right? So, for example, in a globular protein, literally, if you look at a common globular protein like myoglobin or hemoglobin, they look like crumpled up sheets of paper, right? Very somewhat, it appears randomized. There isn't a sort of a regular alignment around a particular physical axis. Whereas in fibrous proteins, those are more analogous to a rope, right? If you look at a rope, you'll see that it has like several little cords that are in it, and they're all sort of twisted around along a central axis, and of course that sort of strengthens the rope, right? That's kind of what fibrous proteins are. And because they're aligned in this specific way, that really helps to optimize the intermolecular interactions and make them stronger. All right. A good example of this, and again, sorry my picture is cut off here, but you can see it on a real computer, is collagen, right? Collagen, as we've mentioned collagen before, it is a fibrous protein that's commonly found in structures such as cartilage, ligaments, tendons, bones and teeth, gums. So all of these have to have a certain amount of durability, certain amount of strength and support, right? Well, because collagen chains can sort of interact and twist around this centralized axis, that means their intermolecular forces are really, really optimized. You have a high accumulation of strength, right? Another example is keratin. Keratin is commonly found in hair, wool, fingernails, the horns of a bull, etc., etc. Again, very strong because they're aligned along a central axis. Very strong mechanical properties, and they're insoluble in water and dilute salt solutions. So, if you ever want to test this, just clip off a fingernail and see if you can dissolve it in water. You're going to be waiting a long time because it's not going to go anywhere. All right. Interesting example. I don't know if you guys have ever heard of this or not, but there's a disease, a condition, called scurvy. All right. Scurvy used to be a real problem, and this was like, when I say real problem, like hundreds of years ago, amongst sailors, people on the open sea. A lot of them got scurvy. What scurvy is a deficiency in vitamin C. All right, so I guess when you're on the sea, on the ocean, on the water, a lot of times they did not have readily available sources of vitamin C. Vitamin C just so happens to be essential for the synthesis of collagen. So as sailors would be out on the sea for weeks and months at a time, a lot of times they would notice that their gums would start bleeding. They would have more weakness in around some of their joints, like their ankles, knees, etc. Wounds would not heal very quickly, nearly as quickly as they would before. And this is all because the lack of vitamin C was causing essentially a lack of collagen. All right, so kind of an interesting example. All right, so then you have globular proteins. Like I said, these are not aligned around a particular axis. These are more or less spherically shaped. Again, kind of resembling a wadded up sheet of paper. These are soluble in water and dilute salt solutions. So in these, what happens is as you form the sort of the spherical fold, what happens is the polar side chains sort of try to arrange themselves so that they're exposed on the outer surface of the protein, because most frequently these proteins are going to be exposed to water, right? So the polar side chains, they like being exposed to water, so they want to be on the outside. The nonpolar side chains are generally kind of buried inside. So in order to accommodate this arrangement, globular proteins have very specific, even though they look kind of random, they're kind of very specific folds. And this also creates certain pockets. And we'll talk about this more with enzymes later on, called active sites, where certain type of things will literally be able to fit in. All right. You usually have quite an abundance of alpha helices and beta sheets. All right. So again, picture cutoff. So look at the full one on your own. This is a drawing of a good example of a globular protein that's called myoglobin. All right, myoglobin is a very important protein. It is designed for oxygen storage. All right, yeah, we have to have it to store oxygen within tissues. So myoglobin, the basics of it, consists of one polypeptide chain. It has 153 amino acids in it, and also one heme group. We'll talk about that just in a second. That one chain consists of 8 different alpha helices, and these are labeled A through H. So you have helix A, helix B, helix C, etc. No beta sheets. 75% of all the residues are found in these alpha helices. All the other ones are found in reverse turns. All right. Within the middle of this somewhere is something called heme. Heme basically is going to be the portion of myoglobin that actually holds on to oxygen. All right. What heme is, it consists of something called a porphyrin. Porphyrin is this big, sort of large, complex organic structure. It has a bunch of connected pyrrole rings. All right. And here's a picture of heme. It's a little cut off, but you can look at the full version on your own. So this porphyrin ring, if you look in the center, it forms like this little pocket. That's where iron is connected. So this has one iron 2 atom that sort of anchors in to the middle here. All right. This iron can actually form 6 bonds. 4 of the bonds anchor iron into the middle of this heme ring. All right? I'm going to skip down to here. All right? It has 6 coordination sites. 4 of them bond to the porphyrin ring. One of them is bound to one of the uramino acid residues found on helix F in the 8th position. It's a histidine. All right? Hold on. I'm opening my book so I can see the full picture of this for reference. One second. Okay. So you can't see it here, but again, look at the full picture on your own. You'll see below this iron, you see that little bond leading downward? That's the one attaching the iron to histidine F8. All right? So that's how it's anchored within the myoglobin. All right? Its last binding site is the one that allows it to bind to oxygen. All right? So the deal is that you have this myoglobin with the heme group. Oxygen can come in and it can attach itself to iron. And that's where it can be kept for storage. All right? Okay, very good. So, one thing that's kind of interesting, though, is that due to the folding, there's another histidine that just sort of hangs above this heme group. Right? It's not connected to it, but just sort of hangs above. It's histidine E7. So, it's a histidine found on helix E at position number 7. All right? And this histidine is actually very, very important. It acts as what we call a gatekeeper. It's literally sort of like the security guard that you have to pass by in order to bind with your iron. All right? So what happens is that oxygen will sort of come in here, and it's got to fit in between this histidine E7 and the iron, right? That makes it a little bit harder for the oxygen to come in. It's got to come in and bind sort of at an angle instead of just coming straight on perpendicularly. So you might think that's bad, right? You know, wouldn't we want it to be easier to bind oxygen? Well, yeah, but there's another factor. And that factor is something called carbon monoxide. All right? Carbon monoxide, you've all probably heard of it before. It's a poison, right? It's very dangerous. It's very deadly. It's a colorless, odorless gas, so we can't smell it. And that's part of the danger of it because you don't even realize that it's around you. We can have, you can get carbon monoxide detectors for your home, right? So that'll indicate, okay, if you're getting to dangerous levels of carbon monoxide, you need to get out. The reason carbon monoxide is so dangerous, in addition to its lack of detectability, is that heme freaking loves carbon monoxide. Much more so than oxygen, in fact. Heme's affinity for carbon monoxide is about 25,000 times greater than for oxygen. So you see why it's so dangerous now. If your heme has a choice of binding to carbon dioxide or oxygen, it's going to bind to carbon monoxide, right? And so, obviously, that's bad because then your body does not get the oxygen that you need, all right? That's just with regular free heme groups. However, in myoglobin, this gatekeeper kind of helps out. The gatekeeper makes it harder for oxygen to come in, that's true, but it really makes it harder for carbon monoxide. So it's more of a hindrance for carbon monoxide than it is for oxygen, right? This affinity, with the presence of the gatekeeper, is reduced down from 25,000 times to 250 times. Otherwise, we'd have some real problems. Okay? So it's a really neat little function there of the folding that allows myoglobin to more efficiently bind oxygen without binding carbon monoxide. All right. We've done primary, secondary, tertiary. Let's talk quaternary. Now, one thing to note right off the bat is not every protein has quaternary structure. Quaternary structure is the interaction between different protein polypeptide subunits within a protein. Some proteins are actually composed of multiple polypeptide chains. This is a globular protein, that's why it's random squiggles. So, we might have this chain. We might have this chain. We might have this chain. And we might have this chain. All separate polypeptide chains, but they're all kind of linked together in this one big unit. All right, so each individual polypeptide chain would be called a subunit. And the quaternary structure is how subunits interact with each other. All right, so if you have a protein that's just consisting of one polypeptide chain, you won't have quaternary. Right? So myoglobin, for example, does not have quaternary structure because it's only got one chain. All right? You can see some of these. These are just examples. I'm not going to go through them with you. What's a good example of this? Well, it's another globin. It's hemoglobin. All right, and this is the one you're probably a little bit more familiar with. Hemoglobin actually consists of 4 subunits, 4 polypeptide chains. 2 of them are referred to as alpha. All right, and then you have 2 beta. The 2 alpha ones are the same. The 2 beta ones are the same. The alphas can each contain 141 subunits, and the beta ones contain 146. All right, so here's a picture. Again, you can take a look at a better picture on a real computer. But each one of these subunits is going to have a heme group within it. Each one of these heme groups can bind 1 oxygen. So 4 subunits times that means that overall hemoglobin can bind up to 4 oxygens. All right? Hemoglobin has a similar but different function than myoglobin. Myoglobin's used for oxygen storage. All right? Hemoglobin also binds oxygen, but its overall function is not oxygen storage. It is oxygen transport. Right? So what hemoglobin does is it'll go to the lungs, it'll pick up oxygen, it'll carry it through the bloodstream to other tissues, and then drop it off there. Then it'll go back to the lungs, lather, rinse, repeat. Right? Whereas myoglobin is just basically stored in the muscle tissue. All right? As a result of this function, or I guess as a result of this activity, it has this function. There's going to be a new term here I'm going to introduce, and this is called cooperativity. And specifically, really, hemoglobin exhibits what we call positive cooperativity. Right? Basically, what we mean here is that whenever this protein binds something, in this case oxygen, if it binds 1 oxygen, its conformation shifts a little bit and makes it easier to bind a second oxygen. Once that second oxygen binds, it makes it easier to bind a third one. And you get a third one, it makes it easier to bind the fourth one. So the more oxygen you bind to hemoglobin, the easier it is for it to get yet more oxygen until you fill up with 4. That's the most it can hold. So this is an interesting graph, and I hate that it cut off here, but again, look at it in its full form. Basically, this sort of shows you how quickly myoglobin gets saturated with oxygen as opposed to hemoglobin. Myoglobin exhibits what we call a hyperbolic curve. It binds one oxygen and basically it's immediately saturated. So it does not take very much oxygen to get that fully saturated. Hemoglobin's a sort of a slower burn, right? The binding capacity is a little bit lower at first, but once you finally get that first oxygen, it gets a little bit faster, gets a little bit faster, gets a little bit faster. So it has what we call a sigmoidal curve. And this is good, right? We want hemoglobin to be as efficient as possible when carrying oxygen. We also want its affinity for oxygen to sort of go up and down depending on the need, right? Because it's used for storage. We want oxygen, or we want hemoglobin to have a very high affinity for oxygen in the lungs where it's picking it up. And we want it to have a lower affinity in muscle tissue where it needs to drop it off. Excuse me, I've got to sneeze. Excuse me. Sorry about that. So, something that's kind of interesting here is something called the Bohr effect. And this is actually an effect of pH within the body. There's a couple of things that can affect the affinity for hemoglobin and its oxygen binding capacity, right? Okay, so in a nutshell, the more acidic the environment is, so an increase in H plus concentration, that makes hemoglobin have a lower affinity for oxygen. So the more acidic the environment is, the more likely is that hemoglobin is going to let go of oxygen. When in the lungs, you actually have a slightly basic pH. That means hemoglobin's very favorable in its binding abilities to oxygen. As you go through the bloodstream and reach the muscle tissues are going to be a little bit more acidic, right? And this is going to cause it to drop it off. So that actually works out very well. All right. Another thing that can affect hemoglobin's affinity for oxygen is carbon dioxide. All right. And this actually all goes back to sort of the blood buffer system. All right. So you remember the blood buffer system involved carbonic acid, the carbonic acid system. And so I'm going to write down a couple of the reactions that we see within that. We talked about them in another video. Oops, that should be liquid, not gas. Okay, so carbon dioxide levels within the bloodstream, that can also affect the affinity of hemoglobin for oxygen, right? The more carbon dioxide that you have in the environment, the less affinity heme has for oxygen. In other words, the more quickly it'll be dropped off. This actually makes sense when you think about it because, if you look at the equilibria here, an increase in carbon dioxide aqueous in the bloodstream is going to shift equilibrium this way and make more carbonic acid. The more carbonic acid you have, the more H plus you'll form, which we just learned reduces the affinity of hemoglobin to oxygen. So they're kind of interconnected. One other thing that also can help this out is a something called 2,3-bisphosphoglycerate. Um, so this is something else that along the way can bind itself to hemoglobin and help to sort of artificially release it. So that's sort of always there. If BPG was not present, even with increased acidity, you wouldn't be able to release much oxygen at all. So that's an essential component. All right, we're almost done here. By the way, this slide is out of place. This slide should have gone before the one above it, so sorry about that. One other thing I want to talk about real quickly is just an interesting example. We talked about all these proteins and that they have to fold in a certain way for them to act the way they should. Of course, disruptions and irregularities in folding can cause different functions, and a lot of times those can be problematic, right? This is one example that's kind of interesting. And this is talking about specifically misfolded proteins in the context of neurological diseases. Um, if you take a lot of the neurological conditions that come along with, older age, you've probably heard of Alzheimer's disease, Parkinson's disease, those type of things. A lot of those are caused by, are signaled by these little plaques that sort of deposit within neurological tissue. They're called amyloid deposits as well, and you can see them on photos of neurological images, neurological structures. These little black portions or these little plaques that have formed, and these are sort of agglomerations or aggregations of misfolded proteins. All right. One really interesting example of this is something called a prion. All right. Prions are glycoproteins that are commonly found in nerve cells, and they're also what we call chaperone proteins. They're kind of unique. As prions are made, as new prions are made, existing prions help to get these new prions folded in the correct shape, right? It's kind of a neat little dynamic, all right? However, one thing that's bad is that sometimes these prions get misfolded. And when they get misfolded, they can cause these little amyloid deposits, these plaques. And what compounds the problem is that these misfolded proteins will then help to direct the incorrect folding of new prions, and so forth and so on. So, if any of you guys have ever heard of mad cow disease, if you haven't, look it up. It's quite the interesting tale. Mad cow disease is a condition that cows can get when they really start acting erratically, do very odd things, have impaired neurological functions and cognitive functions as well. Their movements are impaired. And so there's really nothing that you can do for the cow. You got to just kill it and then destroy it because there's no cure. Also, what kind of sucks is if we eat the beef, or if a person eats the beef from a cow that has mad cow disease, that can infect the person that eats it and also introduce these prions that will start misfolding some of the prions within our bodies as well. So it's very dangerous. Another thing that's dangerous is, normally with meat, with tainted beef and other types of meats, a lot of times if it's tainted by a bacteria or something, you can just heat it up, and it'll get destroyed when you cook it. Heat will not destroy, at least the heat of cooking will not destroy prions. They'll still be active. So that's one example, right? There's commonly found in sheep. There's one called a condition, very similar condition called scrapie. There is actually a tribe, and I forget where it is. It's a very isolated tribe that practice cannibalism. They would actually eat the brain tissue of dead members of their tribe. And so there was a condition called kuru that developed where they were eating the brains of misfolded prion infected tribe members and then causing themselves to be affected. Um, Creutzfeldt-Jacobs disease. That's another example of a human version of this. So again, not going into the weeds here, but just kind of an interesting example here to show you just how severe misfolding within a protein can be. They don't all have fates this bad, but they can have big differences. Okay, so I am tired. I'm sure you are too listening to me, so I'm going to cut it off there. That is it for Chapter 4. If you have any questions at all, please let me know, and I'll be sure to get back to you as soon as I can. All right? Until then, hope you have a great day. Bye-bye.